Hello, students. Okay, so the first problem that I'm going to discuss is a question that was asked on our homework that I believe was due yesterday for April 8th. And it was on the notes for example 5 in section 9.1. And so in this example, it's asking you to use your calculator, and it wants you to find when the slope of this function y equal to 2 natural log of x squared plus 3 is equal to negative 1/2. And they have some steps of how to use your calculator to do that. One thing that I learned from here, which I heard about it, but I never actually applied it, is taking your derivative and instead of actually finding the derivative, allowing the calculator to generate the values of your derivative itself. So usually what we would do is we would go and take the derivative of this function and then set it and then do a separate equation, set it equal to negative 1/2. Here, instead of finding the derivative, the calculator generates the values for the derivative. So let me talk to you about that first. So because that might be new to some of us, let me just show you how that works. So let me start with a more simple function like x squared. So I have that. And then let's say I want to find the derivative of x squared. We know that the derivative of x squared is 2x. So instead of me putting in 2x right there, I am going to write derivative of my y1. So vars y1. Now, if this were a ti, you are going to have to put comma x into your equation here. But for Casio's, you just have to state y1 and then enter. And so now what this is saying is it's going to take the derivative of y1. So now I'm going to draw this. There's my x squared. And now it's drawing the derivative, which is 2x. So we can see that the second graph that it's drawing is the derivative. So now let's go back to this problem. I'm going to write 2 natural log parentheses x squared plus 3. Double check that. Okay, good. And then I already have the derivative of y1 there. Okay, so here we go. Delicious. Okay, so now the first graph right up here is the natural log graph. This second graph right here is the derivative of that natural log graph. So now that I have that, the question is to find out when the slope of the tangent is equal to negative 1/2. So oftentimes we need to solve this equation. So I'm going to say y prime is equal to negative 1/2. And you could go actually find out the derivative. The equation would be then 2 multiplied by 1 over x squared plus 3 times 2x, which would then be 4x divided by x squared plus 3. And so the equation, if you had to do it, would be 4x divided by x squared plus 3 is equal to negative 1/2. But you don't have to do that. I could just look at this and say y prime is equal to negative 1/2. And how would I solve this? I would put this in 1 y equals, in this situation I have y equals to 2. And I would put this one in y equals to 3. So I'm going to go back to this, and I'm going to put negative 0.5 into there. And now it's going to graph a horizontal line, That's the second equation. And then there's a horizontal line. It's really hard to see. So let me zoom in a little bit. Zoom in. Enter. Okay, so now you can see that it intersects here and right about there. So it has two intersection points. So all you have to do is find the points of intersection of y2 and y3. So intersect. And so now on my calculator, it's asking me, do I want to use the first one? No, I don't want to use y1. I want to use y2. So I'm just going to scroll down. There's y2. And so I'm going to hit that one. And then it's asking y3. And I say, yes, that one too. And now it's going to find a point of intersection. And it's taking a while to think. Okay, so there I have the first point of intersection. And I know there's a second one, but it seems that since I zoomed in, it's not giving me the second one because it's not on the screen. So I'm going to have to zoom out again and get the second one. Okay, that's the downside of using the graph. You have to have all your solutions basically on, let me see, can I scroll over? No. So I have to have my intersections on the screen and then it'll give it to me. So, but in any case, here is the solution. So they had you put this in y1, take the derivative, put in y2, then take what you want it to equal and put it in y3, and then they found these points of intersections, which they said they wanted you to find it to the nearest hundredth. And then this figure right here is the equations of the tangent lines graphed at those points of intersection. So at negative 0.39, that would be the equation, and negative 7.61 right there, that would be your equation. And that would be what it looks like for your tangent line. So now the other question that was asked was 2012 BC number 5. That equation right there. All right. So it was, okay, it says the rate at which a baby bird gains its weight is proportional to the difference between its adult weight and its current weight. So I'm guessing the adult weight would be 100 and its current weight would be your B. At time 0, when the bird is first weighed, its weight is 20 grams. If B of t is the weight of the bird in grams at time t days after its birth, then this would be the differential equation that represents the weight of the bird, the rate of change of the weight of the bird. Let B of t be the solution to the differential equation above with the initial condition this. Okay, sounds good. Okay, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So I think that one was fairly easy, and I don't think people had questions on that, but I'm going to put it in anyways. So I'm going to do that right here. So when it weighs 40 grams or 70 grams. So I'm going to do that here. dB dt when it weighs 40, when B is equal to 40. So I would substitute that in, so I'll have 1/5, 100 minus 40, and that's going to be 1/5 times 60, and 1/5 of 60 is 12. So this is going to be 12, and then it's going to be grams per day. That would be the rate of change. And so then I would have dB dt at 70 is equal to 1/5, 100 minus 70. So that's 1/5 of 30. That's 1/5 of 36. So that's going to be 6 grams per day. And is a bird gaining weight faster? Okay, so it's going to be gaining weight faster. Gains weight faster at 40 grams because I would say dB dt at 40 is greater than dB dt when B is equal to 70. I would say B equals. Or you can just write that it's 12 grams, it's gaining 12 grams, which is faster than 6 grams per day. All right, now the next one, it's asking about the second derivative. It says find the second derivative in terms of B. That's the first thing it's asking us to do. So I'm going to go find the second derivative in terms of B. Okay, so second derivative in terms of B. Excuse me. Is taking the derivative of this expression right here. Let me highlight that since it's kind of hidden now. Okay, taking the derivative of that expression right there, because that's the first derivative, so now we want to do the second derivative. We want to do it in terms of B. So I'm going to hold on to the 1/5. And now the derivative of 100 is 0. And then derivative of B with respect to t is going to be negative 1 dB dt. Like so. Which means that this is negative 1/5 dB dt. Now, this would be an okay answer, except for they said they want your answer in terms of B. And that is not in terms of B. That is in terms of dB dt. So we need to substitute that in. So negative 1/5. And then dB dt is 1/5 times 100 minus B. And so when I simplify that further, that's going to be negative 1 over 25. 100 minus B, like so. And that would be your second derivative in terms of B. So now the next thing it says, use your second derivative to explain why the graph of B cannot resemble the following graph. Okay, so they're saying that this graph right here is not the graph of B of t. That's what they're saying. So now we need to think, okay, well, how is this going to help us? Well, we have the second derivative, which I didn't do proper notation. I have the second derivative here. And what does the second derivative tell us about the graph? It tells us the concavity. So I need to figure out how is this going to help me with the concavity. So maybe then I find some critical numbers. So let's see. All right, so then I'm going to go, all right, 0 is equal to negative 1/25 of 100 minus B. So, I'll look at 0 is equal to, what is that? Negative 4 plus B over 25. So that's going to be 4 is equal to B over 25. So that means then 100 is equal to B. Oh, duh, that was so easy. This is when. Okay, so then that means that our critical number is this. So I'm going to say 100, 0, and then that's 0. And so now if I put in some values, I'm putting 0 because the time starts at 0. So let's say if I put in 1. If I put in 1, then I'm going to have a positive. And if, no, I'm sorry, I'm going to have a negative. That's negative. And if I put in, thank you, if I put in something greater than 0, then I'm going to have positive. Which means then, if I look at this, that means for 0 to 100, it's concave down, and for 100 on, it's going to be concave up. So let's see if that matches. Now, remember that this 100 represents B, not T. So I'm looking at the interval from 0 to 100 to be concave down. So I'm looking at this, all of this to be concave down, which I can see that part of it is concave up and then it starts going concave down. So that's why this doesn't match up. So you can state that B, that it's concave down when B is in between 100 and greater than 0. And here, this graph is not. This graph is concave up for part of this interval and concave down for another part of this interval. And that's why it doesn't match up. All right, and then the last part is use separation of variables to find when B of t, the particular solution to the differential equation with initial condition of this. All right, let's do that. So I have dB dt is equal to 1/5 100 minus b. So I need to separate my variables. So I'm going to put dt here, and I'm going to put my b's here. So I'm going to have 1 over 100 minus b dB is equal to 1/5 dt, like so. And then I'm going to integrate. And so then, when you do that, on the right-hand side, I've got 1/5 d, take that back. This is 1/5 t plus c. And then on the left-hand side, this is a linear, and so that means I've got 1 over a linear function right here. So that means I'm going to be doing natural log. Natural log, absolute value, 100 minus b. But if you remember the chain rule, when you take the derivative of this, it will be 1 over 100 minus b times -1, because there's a -1 in front of that b. So I need to undo that -1 right there. And so now I've got the this solved out, and I need to find out my c, and I am given that b of 0 is equal to 20. Actually, it might be easier if I get rid of this natural log. So let me do this. Let me move this negative over. So I'm going to have natural log of 100 minus b is equal to -1/5 t negative c. That part really doesn't matter, but oh well. And I'm going to big E it. So, and so, then I've got 100 minus b is equal to, and I'm going to have a e to the -1/5 t. And where I'm going to say, let a equal to e to -c. Like so. I'm sorry this is messy, but you would have a lot more room than what I have right now. Okay, so I think this will be easier to solve when I substitute values in. So when I put in 0 for t, like so, and I put in 20 for b, like that, then I'm going to end up with 80 is equal to, that is going to go to 1. That's my A. And so then I have 100 minus B is equal to 80 e to the negative 1/5 t. And we are supposed to solve for B of t. It's supposed to be y equals B of t. So I am going to move this over. 100 minus 80 e to the negative 1/5 t is equal to, and add the b. And that's what I would have for my B of t. And that's it. Thank you.